Hello and welcome to this lesson about the logarithm function. I'm Mohamed Kadem Kare. You may download the PDF of this lesson from the website I indicate here, and it will be also indicated in the description below the video YouTube. The outline of the lesson will be firstly to define the logarithm function, then to state its basic properties. After that, I will give you the limits of the logarithm function. The last part of the lesson concerns base 10 logarithm. So let's begin by defining the logarithm function. So we firstly remind some notation here. The set of real numbers is denoted by R, and we denote by R star the set of real numbers minus the number 0. Okay, so this is the set of non-zero real numbers. We denote by R plus the set of non-negative numbers. And finally, we denote by R plus star the set of positive or strictly positive numbers. Now, this is the definition of the logarithm. There is a unique function f from the set of positive numbers to the set of real numbers, which is differentiable and such that f of 0 equals 1 and the derivative of f equals 1 over x. This function is called natural logarithm, and we denote it either ln of x or log of x. So these two notations are equivalent, and some authors prefer this notation, some other authors prefer the other one. So this is the curve of the logarithm function. Observe that the value of the function at point 1 equals 0. We can also keep in mind that the function goes to plus infinity when x goes to infinity. Okay, so as x goes to plus infinity, the function goes to plus infinity. We can also keep in mind that when x goes to 0, okay, when x approaches 0 on the right side, the function logarithm goes to minus infinity. Okay, I will go back to these limits in a few minutes, but the curve permits to keep in mind both the value of the function at point 1, which is 0, but also the limits at plus infinity and at 0. Let's now state the basic properties of this function. The first properties are immediate from the definition. The logarithm of 1 equals 0, and the derivative of the logarithm is 1 over x. Now here is a very useful property saying that the logarithm of the product of two real numbers is the sum of their logarithms. So the logarithm function transforms a product here, to a sum. Keep in mind this property. Similarly, the logarithm of a ratio of two real numbers equals the difference between the logarithms. Also, the logarithm of 1 over y equals minus the logarithm of y. And finally, the logarithm of x power p equals p for the logarithm of x. We can keep in mind this property by saying that the power will come outside the logarithm. So here is an application of this formula. If we aim to calculate the logarithm of square root of x, remind that the square root of x equals x to the power 1/2, so it will be equal to 1/2 logarithm of x. So you see that the properties of the logarithm may be useful in exercises and in many examples. We show now how to solve equations and inequalities with logarithm. If you have to solve an equation in this form, log of x equals log of y, this is equivalent to say that x equals y. Also, logarithm of x is strictly larger than logarithm of y if and only if x is strictly larger than y. This inequality may be also, in the large sense here, is also true. Of course, we have the inequality in the other way, and the inequality will be the same in the left-hand side and the right-hand side. These properties are true since the logarithm function is strictly increasing. Here is an example. Assume that we have to solve this equation here. So the first step is to remind that 0 equals logarithm of 1. And by the first property I stated, that these logarithms are equal if and only if we have this equality. And we can easily solve this equality and find that x equals 1. Here's another example. Assume that we have to solve logarithm of x strictly positive. In this case, we replace also 0 by logarithm of 1, and we get that the solution of this inequality is x strictly larger than 1. So you see how we can solve equations and inequalities with logarithm. The following theorem shows that the composition of a logarithm by a function u has a very simple derivative. This is the formula. The logarithm of u prime, where u is a function which is assumed differentiable, equals u prime divided by u. So this is an application of the property of differentiation of a composition of two functions. We begin by differentiating this function here, which gives u prime. This is the interior function. Then we derive the exterior function, the second one here, which gives 1 divided by, and we apply it to the argument here, u of x. So combining these two terms, we get that the logarithm of u prime equals u prime divided by u. Keep in mind this very useful formula. Here is an application. The logarithm of ax plus b prime will be equal to a divided by ax plus b. Okay, this is an immediate application of this formula. Let's give now the limits of the logarithm function. I have already said that the limit of logarithm of x when x goes to infinity equals infinity. Also, the limit of the logarithm function when x tends to 0 from the right side equals minus infinity. Remind that these two properties are due to the curve, or maybe kept in mind with the curve of the logarithm. So this is the limit at infinity, which equals infinity, and this is the limit at 0, which equals minus infinity. Okay? And remind also that the logarithm at 0.1 equals 0. Here is another useful property. The limit of the ratio of logarithm divided by x to the power p, where p is a positive real number, equals 0. Indeed, this limit here is in a indeterminate form, since here we have plus infinity, and here also we have plus infinity. Okay, so we have plus infinity divided by plus infinity, which is in an indeterminate form. But we know that the power of x prevails over the logarithm. So this is the term that will prevail, and so the limit will be as if it was 1 divided by infinity, and this gives 0. Similarly, if we have to calculate this limit here, we have the limit of this term here, which equals 0, and the limit of this term here, which equals minus infinity, and it is an indeterminate form, but we know that again the power of x prevails over the logarithm, so the limit will be as if it was only this term, and it will be 0. Okay, so keep in mind this very important property that any power of x with a positive power prevails over the logarithm function. Okay, let's apply this property in this example. Assume that we have to calculate this limit here. So observe firstly that it is an indeterminate form, since the numerator goes to plus infinity and the denominator also goes to plus infinity. In order to remove this indeterminacy, the idea is to factorize with the strongest term, which is x squared. So by doing this, we see that we can remove x squared, and for the remaining terms, since x squared prevails over logarithm, this term here will go to 0, and this term also goes to 0 as x goes to infinity. So the ratio here has a limit 1. And this ends this example. We can get the limit of such ratio by factorizing with the strongest term and using the fact that the power of x prevails over the logarithm. Here is another useful example. Assume that we want to calculate the limit as x goes to 1 of the logarithm of x divided by x minus 1. So firstly, that the numerator goes to 0 and the denominator also goes to 0. So this is an indeterminate form. But if we denote f of x as the logarithm function, its derivative is 1 over x, and observe that the quantity of interest may be seen as a rate of range, which that is f of x minus f of 1 divided by x minus 1. Since f of 1 equals 0, we can add it here. Okay, so the limit of this rate of change by definition of the derivative equals f prime of 1. So it equals 1 over 1, which gives 1. Hence, the limit of the logarithm of x divided by x minus 1 when x goes to 1 equals 1. So you see here an application of the definition of the derivative to calculate limits. Keep in mind this technique, it is very useful in many cases. Finally, in the last part of this lesson, I will introduce the base 10 logarithm. So for any positive, strictly positive number, we define the logarithm in base b by log in base b of x equals logarithm of x divided by logarithm of b. So you see that the logarithm in any base is defined from the natural logarithm. In particular, the base 10 logarithm is defined as the natural logarithm of x divided by the natural logarithm of 10. Finally, observe that the logarithm in base b of b equals 1. This follows from this formula here. And in particular, the logarithm in base 10 of 10 equals 1. This ends this lesson about the logarithm. I hope it was clear and useful for you. See you in the next lecture. Goodbye.